Okay, this question is from 2005. Describe the basic principles of ultrasonic scanning, and there are 4 marks here and 1 for quality of written communication. So the first one here then, if you're going to describe this, the first thing I would say here is that you have an AC voltage applied to a piezoelectric crystal. And if you apply that at its resonant frequency, you get the biggest vibrations of the crystal. Then, if you get its biggest vibrations, then this produces a pulse of ultrasound. And they're giving you a mark in the mark scheme for suggesting a frequency. So the frequency would be from 1 to 5 megahertz. They're suggesting is a good frequency to use. Now, at the skin and air interface or boundary, a coupling gel has to be used. And the problem is, if you don't use it, then the sound won't be able to travel into the body. Otherwise, sound pass into the body. It'll all be reflected there. That's why they use a gel. So the ultrasonic waves are reflected from wherever you want to look at. We'll call it the organ. And they're detected by the piezoelectric crystal again in the transducer. Or in the probe. And that produces an alternating voltage. And that's displayed on a computer screen. Now, just for you to see the marks we're going there, there was 1 mark for mentioning piezoelectric, pulse of ultrasound, frequency 1 to 5 megahertz, coupling gel, ultrasound waves reflected, and then how it's detected. There's 1, 2, 3, 4, 5, 6 marks altogether, so they were saying any 4 would have got you the marks. And again, you can see down here, quality of written communication, so you should have written it in complete sentences. Right, the next question is all about X-rays this time. So you can see an X-ray tube. It says the shortest wavelength of X-rays produced by a certain X-ray tube is 14 picometers. Now, if I just write in here an equation, we know that the energy of the X-rays produced is equal to H times F. In other words, Planck's constant times their frequency. But we also know that because they are X-rays, X-rays travel at the speed of light. So we know they travel at speed c, we call it c usually, equals lambda f. So V equals lambda f is our normal equation, but when it's the speed of light we use c. So frequency can also be written as h. Then the f is going to be c over lambda. So if you're getting a shortest wavelength, you're getting a minimum wavelength there. And if you're dividing by the smallest number possible, you're getting a maximum energy out. So it says calculate the accelerating voltage needed to produce such X-rays. And so that means what accelerating voltage is there across the tube between the cathode and the rotating anode here. What voltage do you need across there to make sure that you have electrons arriving here which are going to give up all their energy to produce X-rays with this little tiny wavelength. And the energy that the electrons acquire going across there is given by the equation E is equal to QV, or Q is the electronic charge, which is small e. So that energy from the X-ray tube itself that the electrons get when they're crossing is equal to EV. But then if that electron gets across here and gives up all that energy, then that's equal to hc over lambda. And so we're going to put EV equal to hc over lambda. Rearrange that because we want V, so V is going to be equal to hc over E lambda. And when you put all your values in there, and I hope I've got room, 6.63 by 10 to the minus 34 is Planck's constant, by 3 by 10 to the 8, which is the speed of light, divided by electronic charge is 1.6 by 10 to the minus 19, and wavelength, you have to change it into meters, is 14 picos by 10 to the minus 12. And that gives you an answer of 88.8 kilovolts, or by 10 to the 3 volts, 88.8 kilovolts. The X-ray spectrum of a typical X-ray tube contains a continuous spectrum and also a line spectrum. Why is there a continuous spectrum? How does a line spectrum originate? And there's 3 marks there. So this is this question again. The first thing, continuous spectrum. Is produced when electrons travelling across the X-ray tube give up different amounts of energy. To produce X-ray photons. When they hit the anode. Now in the mark scheme, what they say there is just that they are not decelerated equally. And that's really enough to explain about the continuous spectrum. So if I just draw the continuous spectrum there again, it's something like that there. So you're going to get X-rays coming out of your anode, which have different amounts of energy. They have different amounts of energy because electrons which created them in the first place have given up different amounts of their energy when they hit the anode, and therefore you get this shape, but most of them, you get the maximum number of them occurring in the middle here. So the line spectrum then, and if you remember, that occurs whenever you have some of those electrons hit inner shell electrons. Inner shell electrons in the atoms of whatever the anode material is made from. It causes excitation to higher energy levels. And then whenever they go back to inner shells, they release energy as X-rays. And of course that depends very, very much on the difference between the energy levels. It depends very much on the difference between the energy levels, and that's why you get very, very specific places where you get these spikes here, depending on your material. And so that